Hey Tanya.
Hello.
Hello, how are you?
I'm doing good. How are you?
I'm doing good too. First week of the quarter, how's that going so far?
It's kind of stressful.
Kind of stressful, yeah. What classes are you taking this quarter?
I'm doing Psych
Uh,
41, which is pretty light, and
yeah.
then NPB 110A, and
Uh-huh.
then Chem, and then with ENT with it.
Oh, that's true. Like, dang. How did your winter break go?
It was it was just boring.
Boring, yeah.
Yeah, what about yours?
I got sick at the end, like, because I went to LA and Vegas, and then after that, like the trip, I was sick. I'm still recovering, but I'm much better now.
Oh, that's good.
Mm-hmm. It's good. Did you go to
Yeah,
lecture yet? Uh-huh.
no, my lecture's actually at 1:40, I believe. Let me double check today.
Uh-huh. Okay. Yeah. Uh-huh.
Is that a list of first lecture stuff?
Uh, it's a list of the first things you're gonna be learning about. He's gonna go over nomenclature as well, but I skipped the nomenclature here and like properties as well. I just like wanted to go straight into like reactions and mechanisms.
Okay.
But like we can go over nomenclature or like other properties as well if you want to. When you send the lecture slides to the Google Drive folder, which I will create for you after this session. But we can review the stability of alkenes and um, E2 reaction from 118A. Because the beginning of 118B is gonna be about alkenes, carbon double bond carbons, right?
It's all of 118B on the reactions.
Not all of 118B. The first part of 118B, it'll be first about alkenes, right? Like which are the carbon double bond carbons, and after alkenes, we learn about alkynes, carbon triple bond carbons.
Okay.
Right, right. Okay. You ready to get started with the stability of alkenes, like reviewing something from 118A?
Yeah.
Okay, let's do that. So here are gonna be like the different alkenes I want you to be familiar with. And there's names for these, right? Which I will give to you after I draw them. Okay. Okay. So stability will increase from left to right here, right? Where the more substituted the alkene is, meaning the more R groups the alkene is surrounded with, the more stable it's going to be. The leftmost alkene is going to be unsubstituted, right? Because there's no R groups around it. It's surrounded by four hydrogens. One, two, three, four. This right here is a mono-substituted alkene because there's only one R group surrounding that alkene. This set here is going to be a di-substituted alkene because there's two R groups surrounding it, right? One, two, one, two, one, two. This one right here is going to be tri-substituted because there's three groups surrounding it. One, two, three. This one right here is going to be tetra-substituted because there's four groups surrounding it. One, two, three, four. Right. Now, notice how there's three disubstituted alkenes. There are specific names for each one of those three. If you see the two R groups coming out of the same carbon, we're gonna call that the geminal alkene. If you see the two R groups are coming out of the same side of the alkene, right? That's gonna be the cis alkene. If you see two R groups coming out of the opposite side of the alkene, that's gonna be the trans alkene. Right. So stability is gonna go like this, where the geminal and cis alkene are gonna have similar stability, right? That's why I put this approximate sign, because the two ore groups here are going to have steric hindrance with each other like that. But if you look at the transalkene, the two ore groups are not touching each other. They're avoiding each other. So they're avoiding steric hindrance. But because the transalkene has less steric hindrance than the cis and geminalkene, the transalkene is going to be more stable than the cis and geminalkene. Okay. Okay. Now, when you think of stability, the thing that will be inversely related to that is going to be energy, right? And the form of energy that you're gonna most likely see is heat of hydrogenation, right? Energy. And then you can see that in the symbol, heat of hydrogenation, right? Where the less stable alkene will have more energy, the more stable alkene will have less energy, right? So you can see like a question where it gives you like multiple alkenes, like they could tell you to rank it in order of stability or in order of energy. Right? And you have to be careful because stability and energy are inversely related. Okay. Any questions on this so far?
Um, when it talks about energy, uh, I'm just like confused on what it means.
Yeah. So um that will come more into play when we talk about the first reaction here, hydrogenation. Well,
Okay.
we could go into that here. Let's say we have this alkene right here, right? Which is a di-substituted transalkene. If you see this reagent right here, H2 with any kind of metal like PD catalyst, PD on carbon, right? Palladium on carbon. What that will do is that would convert the alkene into an alkane. It will convert the double bond into a single bond, right? Because if you look at the carbons here of the alkene, they have one hydrogen only. And those hydrogens I'm gonna draw out the same as this right here. But if I color code the H2 here in red, right? We see that those two red hydrogens, one will go for each carbon of the alkene, right? Which is why these carbons here will gain hydrogens right here. And because we're breaking like a pi bond and we're forming two sigma bonds, the overall reaction would be exothermic because we need because we're forming two sigma bonds here. Because in when it's in A, you know how we said pi bonds are stronger than, I mean, sigma bonds are stronger than pi bonds. Like if you think about the overlap between two s orbitals, that overlap is way stronger than the parallel overlap between two pi bonds. Two p orbitals, right? Um, we see here that when we do this reaction, one pi bond is is getting broken, and two sigma bonds are getting formed, right? And in Gen Chem, we learned that to break bonds, we need to gain energy, right? Gain energy to break bonds. And then to form bonds, when bonds are forming, they're gonna release energy.
Oh, I thought it was the other way around. You break it, you put energy into breaking it.
Yeah, when you break bonds, you put energy into breaking it. So that's why the system is gaining energy
Oh, okay.
when the bond is being broken because it's gonna gain energy to break that bond. Right.
Okay, and then
Uh
so that's endothermic,
mhm.
and then the second one is exo.
Yeah, uh-huh. First
Okay.
one would be endo, second one would be exo. Yep. Okay. Okay. So the overall process of this reaction here, hydrogenation, where we convert an alkene into an alkane is going to be exothermic because we're like breaking two, I mean we're breaking one pi bond and we're forming two sigma bonds. And sigma bonds are stronger than pi bonds, so overall it's going to be overall exothermic because we're releasing more energy. Okay. Now, let's say I give you something like this, and I give you something like this right here, and then we do the same reaction, hydrogenation, with H2 and some metal catalyst, like palladium on carbon. We know the reaction will convert the double bond into a single bond, and the overall reaction is exothermic, right? Which one will release more energy? Which alkene here, right? A or B has more energy?
I would say A.
Yep, A, because A is less stable. It's mono substituted. B is more stable. It's tri-substituted. And because A is more stable, is less stable, it will have more energy. It will release a higher heat of hydrogenation, right? Because it has more energy, right? More energy, less stable, right? Whereas B is more stable, meaning that it will have less energy, meaning that it will have a lower heat of hydrogenation, like that. Okay. Okay. Yep. Okay. Nice. There's more for hydrogenation, but we'll get to that when we get to that point. Let's now review alkene synthesis, like how to create alkenes from the first place. The first reaction that you learned is going to be an E2 reaction from 118A. So, this is when we're going to talk about SN2, SN1, E1, E2 reactions. For E2 reactions, the most distinguishing feature is a strong base, strong nucleophile, right? And the strong base, strong nucleophiles that you're gonna recognize are gonna be negative charges on oxygen or negative charges on nitrogen, right? So some examples would be like hydroxide ion, alkoxide ion, OR minus. It could be NH2 minus, um, right? But you could uh distinguish, like you could categorize this more into small or bulky, right? Small, strong base, strong nucleophile, and bulky, strong base, strong nucleophile. So the bulky ones, I want you to know the two that you can see are going to be turbotoxide, right? Which can be shown in many forms. Like it could be like this in bond line form. It could be like this in condensed form, right? And because you see the negative charge here, you don't have to see it in this form. You can see it with like Na, or you can see it with K, because Na or K, whenever you see that, that's a spectator ion that I want you to associate that has a positive charge associated to it, right? Um, so this is a bulky strong base strong nucleophile because we see this bulky R group, the turbobutyl group, right? Which is this TBU over here. Another thing that you can see is LDA, right? LDA, which if you see in bond line form, it would look like this, right? Lithium here, and this nitrogen here with the negative charge, with two bulky isopropyl groups attached to it right there, right? So when you see LDA or turbotoxide, think of a bulky, strong base, strong nucleophile. Everything else that you see with negative charge on oxygen or nitrogen would be small, strong base, strong nucleophile, like hydroxide ion. It could be ethoxide ion. That's gonna be Helix's favorite small, strong base, strong nucleophile. Like he's gonna draw this a lot. Ethoxide ion, right? You could see this NH2 minus. You could see ethane like that, or NH minus like that, right? These right here are small, strong base, strong nucleophiles. Okay.
There's just so much noise.
Yeah. Uh-huh. Any questions so far, Tanya?
No
Hmm.
questions.
Okay. That's
Is my
good.
background noise too loud?
Hmm. No, 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 no.
Okay.
Uh-huh. Okay. Now that is important because let's say we have this haloalkane right here, where we have a good leaving group present, which is this bromine, and we have a secondary substrate because the carbon directly attached to a good leaving group is a secondary carbon attached to two other carbons, right? Um, let's focus on a small, strong base, strong nucleophile with its solvent, like let's say NaOET, and then it's solvent, ethanol, like that. Whenever you see Na, think of a spectator ion, just ignore that. That's positively charged, meaning that whatever is attached to it is negatively charged. So the negative charge thing here is this ethoxide ion, right? This right here is a small, strong base, strong nucleophile. So a small, strong base, strong nucleophile with a secondary substrate is going to be a big indicator of an E2 reaction. Okay. Okay. Now, the substrate here that's directly attached to the good leaving group, I'm gonna call that the alpha carbon, the first carbon attached to the good leaving group, right? Now, the beta carbon is gonna be the second carbon attached to the good leaving group, and I'm gonna draw out at least one beta proton for each beta carbon. We want to be able to form the most stable alkene here. So would we grab proton A or proton B to lead to the more substituted, more stable alkene?
It would be proton B.
Yep, proton B. So this small, strong base, strong nucleophile ethoxide ion here is going to grab proton B, the bond between proton B and this beta carbon here. That bond is going to go create a double bond right there, and we're gonna kick off the good living group at the same time. So these three arrows here are happening simultaneously at the same time. This small, strong base, strong nucleophile is gonna grab proton B. The bond between proton B and this beta carbon is gonna make a double bond here between the alpha and beta carbon, right? And then that's gonna kick off that good living group right there to create us this alkene right here. Nice. Okay. Now let's use the same halocane, which is the secondary halocane right here, but this time let's use tert butoxide, right, with its solvent. When you see K, that's potassium, and I want you to just ignore that because that's going to be positively charged, making whatever is attached to it negatively charged. Okay. Now this right here is going to be a bulky, strong base, strong nucleophile. We have a good leaving group here. We have a secondary substrate here. This is the alpha carbon. These are the beta carbons, right? Now this is beta proton A, this is beta proton B. This bulky, strong base, strong nucleophile wants to grab beta proton B to create the more stable, more substitute alkene, but it's too crowded there, too much steric hindrance, right? We said that this is a bulky, strong base, strong nucleophile, so it cannot reach this beta proton B. It will be able to grab the less crowded proton, the less substituted proton, which is proton beta proton A, create a double bond here between this alpha and beta carbon, and kick out the good leaving group. But that would lead to the less stable alkene, right? Which you might see it referred to as Hoffman alkene, right? And this right here is a Zaitsev, the more substituted one. Okay. Does this sound familiar from 118A, Tanya? Okay, that's good. Okay. So now let's go on to alcohol dehydration, which is another way to create alkenes. And I'm gonna sh show you that through a chart. So alcohol, which I'm gonna abbreviate as ROH, dehydration, is going to have an alcohol, ROH, plus a non-nucleophilic acid. Most likely you're gonna see sulfuric acid, H2SO4, with some heat, right? Which is gonna be shown as this delta or triangle symbol, and that's going to lead to an alkene. Okay. Now, you can have different types of alcohols. Like you can have a primary alcohol, a secondary alcohol, or a tertiary alcohol. And if you have low temp, which is like no heat, or if you have high temp, which is heat, you're gonna have different reactions. Okay? If you have heat, you're gonna favor elimination reactions, right? Like E2 and E1. If you have no heat, you're gonna favor SN substitution reactions, SN2 or SN1. Okay? Okay. Now, let's create this chart right here. Okay. Okay. So we're gonna focus mainly on this column over here because this is more for 118A and this is more for 118B right here. Um, and I'm gonna show you different examples. So let's start off with something like this. H2SO4, heat. And we could also do something like this. Um, let's do this right here. And heat like that. Okay. Okay. So if we look at this alcohol over here, this is going to be a secondary alcohol because the carbon attached to the alcohol is attached to two other carbons. And we see that we have acid and heat. So this is going to be an E1 type reaction. Because we have a strong acid here, sulfuric acid, H2SO4, we're going to look for the most basic atom, right, in this molecule, which is the oxygen of the alcohol. So the oxygen of the alcohol is going to get protonated by the strong acid, sulfuric acid, to get converted into a good leaving group, oxonium ion. Okay. Now, this right here is an alkyl oxonium ion, which is a good leaving group. And because we're doing E1 type reaction, once we have the good leaving group, the leaving group is just gonna leave by itself first, the mechanism, forming a carbocation intermediate. And whenever you form a carbocation intermediate, you have to remember to stop and look out for any carbocation rearrangements, like a hydride shift or methyl shift, right? Look directly to the right and left of it and see if you can make it more stable, right? See if it is more substituted there. This carbocation right here is secondary, so it's already its most stable position. But if you go to the right, that's primary. If you go to the left, that's secondary. So it wouldn't make a difference. So we don't have to worry about any carbocation rearrangement here. Okay. Now, because we have heat, we won't do substitution. We're going to favor elimination here. Um, this is going to be the alpha carbon, the carbon that is directly attached to the carbocation. These are going to be the beta carbons, right? I'm going to draw out one beta proton for each beta carbon, one there, and another one here. Okay. This one here is going to be more substituted, so that's going to be the one we're interested in to create the more stable alkene. So the conjugate base HSO4 minus is going to grab that more substituted beta proton and create this double bond right here between the alpha and beta carbon. giving us this alkene right here, like that. Okay. Um, Now here's another example, but this time it will be more involved because there's an extra step here. Let's do the same first step. Protonate the alcohol to convert that into a good leaving group, oxonium ion. Okay. Now once we have the good leaving group here, kick that good leaving group off, form the carbocation intermediate, right? Now we stop and we see if we can do any carbocation rearrangement, which we see that we can. And I'm actually gonna add an extra methyl group here just to make the answer different. Okay. So we see here this is a secondary carbocation, but we see like directly to the left of it. If we shift the carbocation over there, it could be a tertiary carbocation, which is more stable, more substituted. But we cannot draw that arrow because an arrow represents the movement of two electrons. There's no electrons there, so that would be wrong, right? What we have to do is a hydride shift, draw out the invisible bond with the invisible hydrogen. We're going to shift that invisible bond with the invisible hydrogen to that empty void right there. And that's going to create another void at the more stable substituted position right here. Okay. But now the wedge isopropyl is going to be a flat planar bond because this carbon is now sp2 hybridized, which is trigonoplanar, flat and planar, right? But now we have a more substituted, more stable carbocation where this is the alpha carbon. And actually, we didn't actually need to draw this methyl group out because like the answer would have been different anyway. And these right here would be the beta carbons, the second carbon attached to the carbocation. And the most substituted beta carbon we see is going to be this one right here, right? Which is tertiary. So I'm going to draw out that invisible beta proton right there coming out of that most substituted beta carbon. And then the conjugate base, the HSO4 minus, is going to grab that beta proton and create a double bond between the alpha and beta carbon to give us our most substituted double bond here, like that. Okay. Any questions on this alcohol dehydration reaction and mechanism? No? Okay, that's good. Now the next one is going to be hydrogenation of alkenes. So we talked about the reaction already. But I want to go over more of the properties here, right? So whenever we talk about alkene reactions, I want you to think about something called, let's say, the regioselectivity of the reaction and the stereoselectivity of the reaction. Some will have none, right? So the regioselectivity, the most like important ones are gonna be Markovnikov. You're gonna see the term Markovnikov and anti-Markovnikov. Okay. So when you see the term Markovnikov, I want you to think about just a fancy way of saying more substituted. Okay. When you see the term anti-Markovnikov, I want you to think about just a fancy term of saying less substituted. Less substituted. Okay. Now stereoselectivity, there could be a syn addition, or there could be anti addition. Okay. So syn addition is going to be just a way of saying the two things are going to add on the same side, on the same side. Okay. Anti-addition, that means that the two things are going to add on the opposite side. Okay. Okay. So a lot of these reactions will talk about regioselectivity and stereoselectivity. So they're either going to be Markovnikov or anti-Markovnikov. They're going to either have same addition or anti-addition. And some of them will have none, like no regioselectivity and no stereoselectivity. Okay. So let's talk about hydrogenation here. Okay. So the hydrogenation's regioselectivity would be none, right? Because we're adding hydrogens on both carbons of the alkene, so it doesn't matter like where it is added being added, like the more or less side. But the stereoselectivity of this reaction is going to be syn addition, right? That means that the two hydrogens are going to add on the same side. So, for example, if I have this alkene right over here, right, and then I react it with H2 palladium on carbon, I know that we're gonna add two hydrogens, one for each carbon, right? But on the same side. So what that would be represented like in the answer is something like this. If I make my invisible hydrogens, let's say dashes, these two groups would have to be wedges, right? Like this ethyl group here has to be a wedge. This methyl group here also has to be a wedge if both of the hydrogens are dashes, right? But they didn't have to be dashes. They could have been the other way around. So that's why we could put this symbol here, which means that it is plus in the enantiomer, right? Which I can draw out like this, right? Where the hydrogens could have been wedges instead, like this, like that. Okay. So the reason why the hydrogens add on the same side is because this is gonna be the metal over here, like palladium on carbon, and the hydrogens are gonna like attach onto the alkene at the same time. At the same time, and because they're doing it at the same time, they're adding on the same face, on the same side. And that's why it's syn addition, right? Okay. But when you draw out the answer, you don't have to draw out the hydrogens. You can leave them as invisible. But make sure the stereochemistry is correct for the other group. Okay. Okay. Now, here's a tricky question. There is a major and minor product for some examples. Let's say I give you something like this. What do you predict the major product would look like if you're given this alkene, right, with this reagent here? Mhm. Yeah. So, do I have any advice on starting strong in one scene B in the start? One scene A overwhelmed you in the beginning. You want to prevent that in one scene B. So, um, wait, I'll be right back. I'm gonna get some water and then I'll give you some advice on that. Okay, I'm back. Let me try something. Let me try this new feature here and see if you can see it. So for this problem, you think the PDC attaches to the endpoints where the pi bond is and the pi bond breaks. The pi bond will break, right? And then that would create a single bond like this. And that will be the answer. But I just realized that I forgot something about this problem. Let's say I had let's say ethyl group here and a methyl group here. If I had an ethyl group up there and a methyl group down there, what would the product look like? Think about the stereochemistry here and stereoselectivity here. Like, think about if this ethyl and methyl group would be a wedge or a dash, and think about the surroundings, and think about the stereoselectivity and the mechanism as well. Yep. So they would both be dashes or both be wedges, correct? Because it is syn addition, right? There is a major product though. The invisible hydrogens would stick out on the same side, like both wedge or both dash. The mechanism is that the hydrogens would approach the alkene at the same time on the same side. Um, but where do you think the hydrogens are gonna be sticking out from? Would do you think the hydrogens are gonna stick out from like approach on the wedge or the dash side, depending on what's around the alkene? What's gonna avoid steric hindrance? The wedge side, right? So that would force the ethyl group and methyl group to be on the dash side if the hydrogens are going to approach on the wedge side, right? To avoid steric hindrance. So this one here is actually the major product, even though it looks minor, because we see a lot of groups on the same side, right? We see this terbutyl group, this ethyl group, this methyl group, and this terbutyl group on the same side, and that looks very sterically hindered, but this is actually the major product because the mechanism is that the hydrogens approach on the less sterically hindered side, the wedge side, like that. Yeah, nice. You got it right. Uh-huh. Let's go. Okay. Okay. So for 118B, I recommend following Helix lecture slides like very closely, like understanding it, like every detail, every word, right? And then like whenever you go through lecture, star the ones you don't understand. So then in our next session or when you text me on Discord, just like text me what you don't understand. We could go over that. And then I can send you my notes for 118B that I'm like basing off this from, like from the AETC specialist that I took notes from. And also doing a lot of textbook problems as well. Like I feel like the textbook problems would test you conceptually, right? Which is like I would say a little bit more difficult than Helix style questions, but if you understand the textbook style questions, that means you really understand the material and you'll do well in Helix exams, right? And Helix has three exams. One of them will get dropped. So just like aim to do well in all of them, but know that if you do terrible in one, that one will be dropped, right? Um, let's see here. Also, you could well, like watching other YouTube videos might confuse you because like it might be not the same way as like how Helix teaches it. But going through the ATC worksheets is also nice. The notes as well. And Jokem, the link that I sent you on Discord, that would also explain things conceptually as well, right? Yeah. And also like going ahead, like how you are now, like before lecture is good. Because like once you get into a lecture and he explains these reactions, you've already seen these stuff. So um you're already doing something that's ahead of the curve. So that's good. That's good. Okay. Okay. Yeah. No, shares not YouTube too much. Yeah. Follow slides, understand details. Try not to stick to this lectures, not to YouTube so much. Yeah. Um, yep. Text confusing topics to me, based on the lecture. Textbook problems. Yep. They're harder than Helix, so practice them, understand them, right? A to C, Jochem, review before lectures. Yep. Mm-hmm. It's good. It's good. Yeah. Mm-hmm. Of course. Okay. Next thing that we could talk about is going to be um hydrohalogenation of alkenes. Okay. Okay. See here. Okay. So another name of this reaction that you could see is going to be addition of HX to alkenes. Okay. HX is a nucleophilic acid where X could be like chlorine, bromine, or iodine, right? Like HCl, HBr, or HI. Okay. The regional selectivity of this is going to be Markov-Nakov, meaning the more substituted position. The stereoselectivity of this is none. There's no stereoselectivity of this reaction because of a carbocation rearrangement, right? And I want you to really understand the mechanism as well because on Helix exams, there could be explanation questions which are very conceptual. And to know those conceptual questions, you have to like really understand the mechanism, right? And like why is this reaction like does not have stereoselectivity? It's because in the mechanism there's a carbocation rearrangement, which we'll go over right now. Okay. So let's say we start off simple. Let's say we have uh well, before we get into that, let's talk about alkenes, right? Alkenes are nucleophilic and basic, right? Because there is an area that is so concentrated in electrons because of the double bond right here, right? And we could easily see that through resonance because we see that this bond here has two electrons. If we move those two electrons onto that carbon right there, we can see that that carbon would be negatively charged and this carbon here would be positively charged, right? And we could say that this carbon here can be the nucleophile, or if we moved it the other way, this carbon here could have been the nucleophile, right? So the carbons of the alkene here, like either side, can be the nucleophile, right? But let me ask you this over here, Tanya. If I have this alkene right here, right, which carbon do you think will have w- a more stable carbocation? A or B? Which one will have a more stable carbocation? A, right, because it's more substituted. And because A will have a more stable carbocation, right, I'm gonna draw that arrow right there going to this carbon because that would allow us to have the more stable carbocation like that. So the more likely nucleophile here of this alkene is going to be this carbon right here, right? Both carbons are nucleophilic because like electrons can go on either side, but electrons are more likely to go to this side, right? Because that would lead to the more stable carbocation right there. Okay? So that's important to know because if I, let's say, use the same alkene right here, right? And then I react this with HBr, right? HX, one of the HX right there, that's a strong acid. And we said that this alkene here is a nucleophile and a base, right? But like we said, this carbon here is going to be the more likely nucleophile or base because that's going to lead to the more stable carbocation intermediate, right? So this carbon here is going to be the base that's going to get protonated by the HBr, kick off the Br by breaking that bond right there, and lead us to this carbocation intermediate right here, right? Where this carbon here has a proton, but I'm going to leave that as invisible, which came from the HBr. Okay. Now, once we have the carbocation intermediate right here, we always have to stop and see if we could do any hydride or methyl or alkyl shift. In this case, it's already at its most stable position, so we don't have to worry about that. Then the nucleophile Br minus comes back and attacks that carbocation to give us our final answer here, right? And because this is a flat carbocation, the Br could come on the top side forming a wedge product or the bottom side forming a dash product. But we don't have to put wedge or dasher because there's no chiral center. This is not a chiral center because there's two of the same methyl groups coming out right there. Okay. Now we see why this is Markovnikov reaction because the nucleophile here, which is the bromine, attached on the more substituted side of the alkene, right? Which is this carbon right here. That's the more substituted side, aka Markovnikov side. Okay. Any questions on this mechanism so far, Tanya? Why did the least subside attack the HBr? Yeah, so the least subside of the alkene here attacked the HBr, specifically the H from the HBr, because the resulting intermediate led to a more stable carbocation. Like if I kept track of this less sub carbon here, right, which grabbed the hydrogen, that led to a positive charge on the more sub side. If, however, like let's say we use the more sub side to grab the hydrogen from the HBr, kick that out, where the more sub side will have the hydrogen instead, and then this more less sub side will lose a bond, right? That less sub side will have the carbocation, which is less stable. Right. So we used the less subside of the alkene to grab the H, Br, so then the more subside can lose a bond and have the more stable carbocation at that position. Okay. Did that answer your question, Tanya? Yep. Okay, that's good. Okay. Let me give you a practice problem to practice with here, which is going to be a little bit more difficult than the one that we just did. But I think you could do it. Let's see here. Let's do this. Like this, okay? And let's react this with HCl. Given this alkene and reagent here, describe to me step by step what do you think the mechanism is gonna be like? Yep. The tip attacks the H and goes and yep, and a hydra shift. So the left subside or the tip attacks the H, kicks out the Cl, form the carbocation intermediate, right? Where this carbon here is gonna lose a carbon, I mean lose a bond. So because it's losing a bond, it is going to be positively charged, right? And then once we have this carbocation intermediate, we stop, see if we can do any hydride or alkyl shift. And in this case, we can. like you said, we could do a hydrogen shift by drawing out that invisible hydrogen, shifting that hydrogen over onto that carbon, which will lead to a more stable carbocation intermediate here. Okay. And then from here, once we have the more stable carbocation intermediate, what's the final step? Mm-hmm. Okay. Now the Cl minus here will come on, attack onto that carbon, and give us this final product here, where this chlorine here could have attacked on the top side, giving us a wedge product, or the bottom side, giving us a dash product. We should make sure if this is an enantiomer, but there's no enantiomer here, there's no Carr center, right? This is not a Carr center because this is gonna be the same as that. Okay. Nice, you got it, Tanya. Good job. Okay. So the next thing is gonna be hydration of alkenes. Okay. Let's do hydration of alkenes. Now, when you're learning these reactions, right, you know exactly what to do, mechanism, because you've just seen it. But when you're on a test situation and you see a lot of problems, like predict the product or mechanism, and you see a lot of like alkenes and different reagents, you might get confused about what reaction to do. Like, yeah, did you experience that at the end of 1A when you saw like a lot of similar reactants and reagents put together, but then like there were so many reactions you didn't know what reaction it was? It's gonna be similar to that, right? Where you're gonna see a lot of alkenes and a lot of different reagents, but you have to like associate like the alkene and the reagent with the reaction name, right? And then from that, you have to like really understand what's happening behind the scenes, right? Like for this, right? To understand what's happening behind the scenes without knowing the reaction name is that we you have to understand that this alkene here can be nucleophile or base because there's a lot of electrons from this double bond, and this HCl here is a strong acid. So because you see a strong acid and a base, we're gonna do an acid-base reaction in the first reaction, right? But we have to do so that would create the more stable intermediate, the more stable carbocation. So like there's a lot of like conceptual things going on behind the scenes here that you have to understand that will help you figure out what's gonna happen in the reaction on the test, right? Felt like I needed to do more practice to memorize than one is an A. Yeah, yeah. It's a lot of like memorization, but with understanding concepts like this, like how I just explained it to you, that should be able to help you if you get stuck. Like if you get stuck, just like break it down piece by piece, right? Strong acid here, base here. What's gonna happen, right? What can I do? Like that, right? Yeah. So when you practice, like don't just like go through the practice just to get through them. Like actually try to understand conceptually what's going on behind the mechanism, arrow by arrow mechanism in the practice, right? Another thing that could help is like teaching your friend like or friends like through the practice as well, like conceptually, right? Okay. So hydration of alkenes is gonna be like very similar, right? So based on what I just talked about, I'm just gonna give you an alkene, right? A simple alkene, and I'm gonna give you the reagents and see what you think is gonna happen between them. I'm not gonna teach you the mechanism yet. I'm just gonna see your ultimate intuition on what you think is gonna happen. Okay? So when you see this alkene right here and you see these reagents, what is the first thing that comes to your mind? What do you think is gonna happen first? Yep. So this alkene, there is a more sub side, which is this side, and this there is a less sub side, which is this side. And what do we say alkenes like were in Ochem? Like they're like because of this double bond here, there's a lot of electrons, and because there's a lot of electrons there, they could be nucleophile or base, right? Nucleophile or base. What do you think that would do with these reagents here? Like what is this? Yep, it's a strong acid. So if it's a strong acid, are you thinking of acid-base reaction? What are we gonna protonate here with the strong acid? Which side? The least subside, right? Because that would lead to the more stable carbocation intermediate, which is right here. The least subside here is grabbing the proton, which is this invisible proton here, making this more subcarbon lose a bond, which is why it has a positive charge now, and that's good because that's the more stable carbocation intermediate. If we use the more subside to grab the proton instead, right, which would grab that proton there, the positive charge will be on the less subside, which is less stable, right? Now, once we have this more stable carbocation intermediate, we always have to stop, see if we could do any carbocation rearrangements. In this case, it's already a small stable position, so we don't have to worry about that. Okay. Now from here, right, the conjugate base is gonna look like this, the HSO3 minus, where you notice how this negative charge here, it can do resonance like two times with the two double bonds right there. This is a weak base, like it's stable because of resonance. But we do have another nucleophile floating around here, which is the water, right? What do you think is gonna happen between the water and this carbocation here? Yeah. What do you think is going to happen between the water molecule that has an oxygen with pairs of electrons and this carbocation intermediate here? Yep. So this oxygen here with pairs of electrons and a partial negative charge will be the nucleophile. This carbon here with the full positive charge is going to be the electrophile. So the nucleophilic oxygen atom of the water will attack this electrophilic carbon right there, creating a new bond between this oxygen and carbon right there, giving us this intermediate right here. So this right here that I just drew out is the new bond between that carbon and oxygen, right? This is the new bond right here that we formed. This oxygen here is still attached to two hydrogens, like that. And because it has three bonds and one pair of electrons, it's positively charged. What the final step is like we could bring in the conjugate base to deprotonate and neutralize the positively charged oxygen to give us our neutral product here, like that. Right. And then we could reform our acid catalyst, H2SO4, from that as well. Okay. Okay. So any questions on this so far, Tanya? This mechanism and reaction? No, okay, that's good. So notice how like if we were to add like let's say from the product and go to the reactant, if we did like H2SO4 and heat, that would be dehydration. Like the first like one of the first things we did at the beginning of the session, if you have an alcohol with acid and heat, that would do dehydration to create the alkene in the E1 type mechanism. Right? Yeah. So this right here is dehydration, and this going forward is hydration. Right? Hydration, dehydration, hydration, dehydration, hydration, dehydration. Right? Yeah. Dehydration because we're adding like heat with it as well. Hydration because we're adding water. Okay. One it should be is a lot of reactions and mechanisms. Like the first midterm will have like over 10, like over like it's gonna be like around 13 to 15 reactions and mechanisms. Yeah. It is a lot. But if you understand the things behind it and do a lot of practice, it should be good. At the beginning, it's very overwhelming, but like just break it down one by one for each reaction first, and then see a lot of practice problems. Like just see a lot of practice problems from textbook AUTC, and Helix practice exams and lecture slides, and then uh I'll create similar practice exams as Helix as well. Once you do a lot of practice, and then you could test your knowledge on these reactions as well before the midterm. Yeah. That's good. And I'm thinking that the Kahoot nights could be based on these sessions. Yep, Kahoot this Saturday. Does 5 p.m. work for you this Saturday? Yes, okay, that's good. 5 p.m. Yeah, it could be based on these what we went over today, like the Kahoot nights. That's perfect. Uh-huh. Yep. So you have time to like look at the notes, which I'm gonna post on your Drive folder, and then review it, and then prepare for the Kahoot night. Yeah. Let's go. Excited too. Yep, of course, Tanya. Yeah. Yep. You too. Have a great day.